Today we finish at 1 o'clock because of the ceremony, and we will start by cleaning up the subject of X-ray diffraction, which we started in the previous lecture, and hopefully we'll go over now and speak a bit about the properties of real lattices, meaning lattices that are made out of these kind of things. And I asked it to appear on the whiteboard for the simple reason that I want to annotate a few things here. Okay, so we had two different conventions of calculating when a peak will appear in the scattering of X-rays. One was the Bragg formulation, where basically we defined all kinds of surfaces on the lattice and calculated when will we have interference between them and got the angles for which we'll get constructive interference. Okay, the other formulation, which is equivalent at the end of the day, but to my taste much more useful and transparent, is the von Laue's formulation, where basically the statement is very, very simple. Okay, so where G is a reciprocal lattice, and K where n vector is just a unit vector in the direction of the propagation of the incoming wave, and K prime is a unit vector in the direction of propagation of the outcoming wave. Okay, so what do we do when we get a lattice? And the question is, where do we expect to see constructive interference or Bragg peaks? Well, the game is very clear. Calculate G, get information about the incoming and outgoing direction, check if they are equivalent. If yes, you have zero peak. If not, you won't have zero peak. Okay, let's see a very simple example. Simple cubic. Okay, and to make life for me even simpler, 2D. Okay, we calculated the reciprocal vector. Simply okay, and now we can
X at Y.
X and Y, of course, thank you. And now we can plot this reciprocal vector points. I will how will we do it? Simply x, y. And the distance is always 2 pi over a. Okay, that's all the reciprocal vectors. How do I see it? I pull a vector from the center to each point, and each such vector is the reciprocal vector. Okay, now I come and ask, will I see a peak? Okay, no problem. Give me incoming and outcoming directions, and I'll be able to answer it. Let's take a very simple example. Let's say okay, I'm incoming in the x direction and outgoing in the y direction. Well, that's not yet defined. I have to say something about lambda. Before I say something about lambda, I can't answer anything. Nevertheless, I can see something that's very important, and it's something that I have emphasized in the previous lectures. If lambda is much smaller than a, much larger than a, whatever this lambda is, it will look something like right? Because 2 pi divided by lambda is much smaller than 2 pi divided by a. That's what I told you. Lambda is much larger than a. No matter what directions will I choose or the exact value of lambda, I will have no Bragg peak. Just because all these will fall in a distance smaller than the distance to the first points here. Okay, so that's a mathematical illustration of what I said in the previous lecture. In order to see peaks, in order to get some kind of constructive interference in a direction different than the incoming one, the only way is to have a wave function within, or now I can emphasize it even stronger, smaller than the distance of the lattice A. Okay, so that's the reason why we need X-rays. X-rays are of order of an angstrom. Distance in typical lattices are within order of 2 to 5 angstroms. Okay, so for X-ray, I have a probability of choosing a direction that will fall on a Bragg peak. Okay. So let's take the case where lambda is okay, a nice simple case, and there I see because of minus lovely, I have here a nice reciprocal vector, I will see a peak 90 degrees to the incoming wave. Okay, what can I conclude from this game? Until now we played very, very simple game. Basically, let's say I'm starting with a given incoming lambda and going through an outgoing lambda. The same outgoing lambda in a other direction. Do I have a large probability of seeing a Bragg peak? No. The chances of, if I just choose some kind of lambda, choose two directions and know nothing about the lattice to land exactly on a Bragg peak is extremely small. So just choosing a lambda, choosing directions and expecting to see a Bragg peak is not a good way to investigate a structure of a lattice that we know nothing about. Now, we have to improve our search here, basically. One simple way of improving our search is to sweep through a range of lambda. That is not so surprising because the usual X-ray machine doesn't put out a very sharp value of lambda. Gives you a Gaussian distribution of lambdas or something like that. So part of it is built in your machine. That helps because if I'm, let's say, sampling a segment of lambdas, you see that I have a bigger chance of landing on a Bragg peak. Another thing that we can improve the search is basically rotating, or first of all, before rotating, just accumulating data on many outgoing K primes. What are you doing really? You're putting either nowadays a detector, the good old days a piece of film, at some direction, but it's not exactly K prime. It has a whole range of K primes. So again, if you're taking a big picture, you have a larger probability of hitting upon a Bragg peak. So that's a second direction. A third one is rotating. Now, what is easier to rotate?
Lattice.
The lattice, of course. A detector is a big, bulky thing. It's stuck somewhere from your ceiling. Well, you can mount it on something like this television, changing a bit the direction, but that's not easy. Rotating your sample is much easier. Now you have another trick that you can play if you have a good detector, and that's grounding your lattice into powder. What do you gain and what do you lose by it? Your size of your lattice becomes much smaller, therefore the amount that will be scattered of it will be smaller. But on the other hand, if you have a powder, you have every orientation in this powder. So basically, without rotating anything, you get all possible rotations of the powder within one direction. So all these different methods have names, since I don't perhaps one of you will become a crystallographer, and the rest of you won't remember anything about this lecture, and those of you who will become crystallographers will study it again and again. I won't go into all these methods have names. Changing lambda is von Laue, changing directions is Euler, doesn't matter. For all this, the whole subject, for those of you who want to get into it deeper, appears in the book that I said is the book of this course. Everything that we went over in the previous week and this lecture appears there, and more. More is for whomever is interested in it. Whatever was covered in the lecture is within the material of the course. Since we are short in time, I won't go into some more examples that we did in previous years here in this chapter. Okay, so basically the most important thing that you should carry out of this lecture is the following. Incoming, outcoming, distance of a reciprocal vector, and we know how to build a reciprocal vector. Therefore, anything else here comes down to calculating the reciprocal vector, knowing something about the incoming and outgoing waves, and a simple vector addition or subtraction in this case. Okay, straightforward. Physics. We have three things in the descriptions that I gave you that are incorrect. One, what happens if my lattice is not a simple lattice but a Bravais lattice, which occurs a lot in nature? So I don't have one point that scatters the incoming radiation. I have several points depending on the structure of my primitive unit cell. Didn't take it into account. One thing. Second, atoms are not point entities. They have some width. What is relevant to the width? We have to understand what is doing the scattering here of the radiation. What interacts with radiation?
Electrons.
Electrons, charge. So what I care about is more or less where will I find electrons around this point, which has a width, as you know from quantum mechanics, well, not those who studied in my course because that wasn't covered, but within half an angstrom for the hydrogen atom to 1.5, 2 angstroms in heavier atoms. But it's not a point, it's something with a width of 1 or 2 angstroms. How do we treat that? And the third thing is we happen to live in finite temperature. But we don't happen, we couldn't have lived at 0 temperature, but we live at higher than absolute 0 temperature, meaning these atoms move. They don't move as violently as a gas, but they still move. Lattice vibrations, phonons. So when we're taking a picture, these guys are moving during during taking the picture, and as you all know, if you take a picture with something that is moving during taking the picture, you get a blur. So that will blur also the Bragg peaks. Okay, the first two corrections I'll do in this lecture. The third one, since we haven't yet learned what's a phonon, we'll have to wait till we learn what's a phonon. Okay, so that's the next steps that we're going to do. Okay, so let's tackle the fact that we have a Bravais lattice. Okay, so what does it mean that we have a Bravais lattice? From each point, for example, a point appearing here, we have actual physical atoms sitting at locations signified by D1, D2, vectors from the lattice point to the actual position of the atoms. Okay, that's the basis of the Bravais lattice, which we defined in the previous lecture. Okay, so what do we know? We know that if we are just treating the lattice points, this should be fulfilled. By the same logic that we got to this relation, I'm saying that if we add points which are not at the lattice point, the distance between them again should behave as expected from a reciprocal lattice, because I want them to always contribute in a constructive way. So, if I'm looking on what happens to a wave that is scattered, let's say, from point D1 and D2, or generally Di and Dj, dot represents a scalar multiplication. We're dealing with vectors here. It's the same. Replace this by the points R1 and R2, and it's the same equation that gave us the previous behavior. What is that? Basically, the distance in the path between scattering on Di and scattering on Dj, and we want it to become 2 pi, and this handles the 2 pi. Yeah.
Can you repeat what we are trying to find?
I'm trying to find what happens due to the fact that I'm not scattering off a lattice point. The lattice point is basically an invention that I put into the system in order to get a lattice. right? I add something with 2 or 3 atoms that are not repetitive, right?
Okay.
Simplest case.
רגע, ה-D1 ו-D2 זה המרחק מהנקודה שאני עושה חדשה, או ש...
Just a moment, I'll try to color.
So you injected somehow atoms
Ju-
to the...
Just a moment. Let's say I have okay, that's a one-dimensional lattice. Is it a lattice? No,
Two lattices.
it's not a lattice because A sees a B2 is right and B sees a A2 it's right. It's not the same environment. So I say, I know how to rectify it. Let's build a lattice unit of this kind. Okay, and this will represent a lattice because if I'm looking on those two together, okay, how do I create a Bravais lattice? I decide on some point which I'll call its center. Okay? Where do I put it?
Wherever you like.
Wherever I like. It's like defining a basis. Okay, so I decide for some stupid reason to put it here. Well, it's stupid because it would have been mathematically simpler to put it on the A or on the B, but now for illustration I'll put it somewhere between A and B. For these blue axes, I have a lattice. So that's my lattice. Now I go and calculate the reciprocal lattice, right? And then I want to calculate scattering of this reciprocal lattice. And then you stand up and start shouting, look, this point has nothing to scatter a wave on it. It's a pure fiction that you put in for mathematical reasons, right? Actual scattering occurs either from A or from B. Not from them both, not from this blue point. Say, right, you're correct. How do I rectify it? Okay, first of all, I have to describe where is the physical location of the atoms, right? So I create a basis. Tell you, go to the lattice point, add the vector dA in order to find atom A, add the vector dB in this case in order to find atom B. Okay? That defines all the physical points in this lattice. So far so good? Okay, now I'm asking, okay, scattering happens, right? It happens of the atom. So it means that there is a distance within the same lattice point between something that scatters on dI, in this case dA, and dB, right? What is the difference? What's written here? It should, in order to be constructive, the phase difference should be 2 pi. That's what's written here. Okay, so I get if I write down all these amplitudes, let's assume I have n different atoms in this unit cell. I'll get an addition, a multiplication of the amplitude by these phases. If I want to know the intensity, what do I do in waves? Square, absolute value square, or value times conjugate of the value. So, what do I do? I go and calculate all the possible Bragg peaks from here, multiply them with the additional amplitude that I received due to the fact that my lattice point is not really the scattering center. That's all.
What does the SK mean?
How much is the... If I had just one scattering point, I would get a Bragg peak at this point, right? Mm-hmm. But now the Bragg peak is multiplied by an amplitude squared.
Okay.
And that gives me the effect of having a complicated object here, not one point, but 2, 3, 4, 5 points. Yes?
What if we had more points in the unit cell? Like, how is the term will change? Like the di minus dj?
Each one of them. Therefore, I multiply by the sum here. If you sum it and square it, you get all directions.
No, not the sum, like the equation above.
No, that's between two particular points in the cell. But I didn't say all of them have to give you 2 pi in order to have full constructive interference, which basically is taken into account here. I'll do an example, and I think it will help you to see what's happening. BCC. Okay, but I'm...
BCC is a lattice.
Excuse me?
BCC is a lattice, no?
Right. What did I say in the previous 5 minutes ago? What do? You find G, you find D?
Yes.
Okay, so now you're looking at me and asking, BCC is a lattice, right? But I'm lazy. I don't want to do BCC. I'm telling you, BCC is equivalent to a simple cubic.
2D.
No, 4D, 3D. We're not yet in 4.
4D, you can't really do any experiments with 4D.
Well, according to some versions of string theory, we are in 10 or 11D.
not dealing with that. It wouldn't be on the scale of the crystals anyway. Crystals are too big for that.
Right.
Was right.
So in 4D, the only way we can do experiments is in silica, which means on your computer. You can simulate a 4D.
Oh,
experiment.
yeah. But you can't do actual experiments, physical experiments.
Okay.
Well, unless something radically changed, not ever. Okay. So, how do I turn a BCC into a simple cubic? I decide that BCC is a simple cubic with 2 atoms per unit cell. I didn't have to, but I'm allowed to. Like choosing a base. I can choose whatever base I feel like. My mathematics should give me the same answer for any physical entity that exists, right? Okay, so how do I change a simple cubic into a BCC? Okay, first of all, right first R. Okay. And I have two basis vectors. First is on the lattice point.
Can you show us how does it work? The cube?
What happens in a base center? You add a point in the middle, okay? So for each existing atom, you have an additional atom, right?
Yes.
So 2 makes sense. Right? From a corner to the center, you move half a lattice to the left, up, and right. That's exactly that. So SC is a BCC if you add an additional basis point at the middle, which is exactly what I did. I'm doing it in the simple cases because that's easy to envision. Okay, great. So I start my procedure. First of all, reciprocal lattice. Now you can see that perhaps I'm not so crazy at treating a BCC as a simple cubic because I can write down the reciprocal vector very easily, and if you remember from the previous lecture, took not tremendous but some work to write the reciprocal lattice for the BCC or FCC case. Okay. So far, so good. If it would have been just a simple cubic, go back to the red enclosed box and check if you have a brag peak. But we have here something, this S known as a scattering factor. And what did they tell me to do? Add and then square it. It's important to do it in that order. First add all points, all basis points, then square it. Or because the other way around you lose interference between different points. Okay. Here I'll write down let me write it down fully. Okay, I just wrote it down. Why did I write it down? To remind ourselves that we have to do here vector multiplication. Okay, so what is the first term? What? Okay. What is the second term?
מינוס 1 בחזקת n1 עוד n2 או n3.
Okay, right. I'll do it in 2 steps for whoever needs it. So first of all of them are a over 2 times 2 pi over a. So I'm left just with a pi. Okay. What's e to the power I pi? That's one of the most beautiful expression in mathematics, according to some people. So, okay, back to the thing. We'll have either 0 if n1 plus n2 plus n3 is odd, or 4 if n1 plus n2 plus n3 is even. Okay, so basically all odd points here don't produce a Bragg peak. So this is odd, this is odd, this is odd, this is odd, these are even, this is even, odd, 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 odd. And it would have been 3D, so continue it into the third.
3D checkerboard.
Right. Why did we get that result? Basically, think about it. If I have BCC, the typical distance between lattice point is A over 2. In one of the dimensions, the length. The corresponding simple cubic is 2A. Reciprocal is 1 over that, right? So I've added points that shouldn't contribute by looking on a SC, on a simple cubic version instead of a BCC. My structure factor takes care of it and kills it off. And I get exactly what I would have gotten if I would have created a really complex sentence structure. If I would have used directly the BCC. Both of them give the same result, because they're the same description, but in the simple cubic I added points and then subtracted them.
So it's always easier to just try to use a simple cubic with.
If for FCC and BCC, yes. In other cases, not always. Okay, we're running short on time. Yes.
Because the unit cell, it seems like it has less of the second type, or less of the one in the middle. Well, maybe it's not second type, but if it was a second type, it has less of the base elements.
It has less scattering points. Less scattering points, less points on the reciprocal vector.
I basically made the unit cell big.
Right. And you add superior points that the structure factor killed out. Now, since we're running short on time, I won't be able to do what happens from the finite width of the atom. But actually, it's very similar. We'll do it within 5 or 10 minutes of the beginning of the next lecture. Basically, instead of having definite points, I have a smear around, instead of having a lattice point, I have some smear around this lattice point with some spatial distribution. Same things, just an integral. Add a weighing of the contribution of this point, giving the density of electrons. But all the rest is the same. So, at the end of the day, these two modifications enable us to work with a Brevis lattice or a lattice of components that are not point-like, but have a finite width. Okay, and unfortunately, next lecture, I don't believe it will remain here, but so.
Especially considering next lecture is next week because
But on the other hand, Monday, Tuesday, there is no lectures at all, but Wednesday, Thursday will probably.
Wednesday, Thursday, so yeah, so this still overall would still be longer.
לא, לא בטוחה שנדע.